Okay, now we will also talk about conformal test martingales, but compared to the previous talk, we're going a step back. We're again talking just about testing, from prediction to testing, not from testing to prediction. So let me remind, there were several talks yesterday about this, but however, how conformal martingales works. We start with some observations. So there is a sequence of observations where, and in this picture we model a situation where there is a change point in the middle. So there were normally distributed ID, normally distributed data before, and there are ID normally distributed data before, but they are slightly shifted in the average. Then by online conformal prediction, they are this sequence of observations. In this example, they are one-dimensional. More generally, they can be examples. Yes. Then it is transformed into a sequence of p-values. And while the ID assumption is hold, these p-values are distributed this way, perfectly uniformly from 0 to 1. This is a perfect uniform distribution from 0 to 1, while then after the change point, they begin to concentrate here. So this is not quite. So this is not quite. So this is not quite. P-values are lower. Right. And do you hear me?
Yes.
And then a conformal. And then a conformal martingale is playing against this. It is basing on these p-values, and it is playing against the assumption that p-values are distributed uniformly, and therefore it starts to grow quickly immediately after the change point. This is the scheme of the conformal testing martingale, and in this particular work, we assume that the information is that the whole information about the data generation mechanism is available. It is open. So we know where is the change point, what was before and what is after. And all this information is open and can be used for constructing the conformal testing martingales. You may ask why we're doing this, because this makes the task very easy for the conformal testing martingales, because for example, before the change point, we can refuse to play because we know that there is nothing to catch. And this is why the martingale doesn't lose anything before the change point. But the question here is transferability of the knowledge into the language of conformal testing martingales, because the degrees of freedom in the conformal test martingales are limited, actually, because there are only two things which can be tuned. First is the conformity or non-conformity measure function, which is applied on this stage to calculate p-values from observations. And the second thing is just the betting strategy to go from this picture to this. But the betting strategy is just a function defined on the interval. So the question is whether this hint we have about the whole data distribution, the whole generation mechanism, can be fitted into this language of conformal testing martingale. Yes, and this poster shows that the answer is, this work shows that the answer is positive. In these examples, that this language of conformal test martingales is universal enough. What we do, here are some of the models which we consider. Gaussian distribution, normal distribution change one of these parameters, and we also add other kinds of distribution, exponential distribution, and something some distribution which is close to uniform. So there are three models of change point detection. And we use some theoretical benchmark, which is taken from this, from the paper, Conformal Testing in the Linear Model Situation. That is known to be a result which gives upper bound for a possible martingale growth, even when it is not conformal test martingale, just for any martingales, because the benchmark is determined by the distribution itself. It can be calculated this way from the density functions. And we know the density functions. I mean, density function before the change point is d1, the density function after the change point is d2. And so there is some benchmark. And in our experiments, we show that it is practically reached. So that the difference between the benchmark and the result, this is the principal table, it is low enough. And furthermore, it further increases if we increase the resolution, the accuracy of our approach. So, as I said, to determine conformal test martingale, we need two things: non-conformity measure and betting strategy. And on each of these stages, we use something natural enough. As a non-conformity measure is based on the Neyman-Pearson statistic, on the ratio of the densities, which is natural enough in this case, as I said. And the betting function, well, the betting function is mostly taken from the plugin, so-called plugin approach for martingales, which was published earlier, which means that the betting function is actually the same as the empirical density, as the density of the p-values of the distribution of the p-values in this situation. And this density is calculated empirically. Here, there is also a detail that density function, we also use so-called isotonic regression to normalize on the stage of calculating the density function, but it mostly plays the role of smoothing. Because, well, we can expect that the density function of the p-values is a monotonically decreasing function. Therefore, for forcing it to be monotonically decreasing by isotonic regression, this works as a good non-parametric way of smoothing instead of kernel density estimation and other standard density estimation algorithms. But so it is not so principal details. All right. Right. So here are the results. We compare these three models with some variations of the parameters. So, for example, for normal distribution, we tried to move the center. We tried to move it to keep the center while changing the variation. Variation is increased, variation is decreased, but there is no actual problems in any of these cases. All right. Therefore, a conclusion is our experiment supports the hypothesis of conformal testing martingale being a universal approach for testing martingales, as far as the knowledge of data generation mechanism can be translated into the language of nonconformity measures for conformal test martingale. So we show that this translation is possible. Well, next principal step, I think, may be modeling more complex ways of concept drift, because change detection is a very simple model. Yesterday, there was another talk about gradual change, incremental change, and so on. And for this case, while this Newman-Pearson statistic is fitted exactly to momental change point. But I think, so maybe what we have to do is to model different situations of a more complex concept drift, and to find what are optimal non-conformity measures, non-conformity measures in these cases to be used. Okay, yes, I finished here.